Hello everyone, thank you for watching our video. My name is Brent Griffin. This work is done in collaboration with Jason Corso, and today I'm going to be talking about our work on learning object depth from camera motion and video object segmentation. In this work we combine video object segmentation with uncalibrated camera motion to estimate the depth of segmented objects. Camera motion can be obtained from robot kinematics or vehicle odometry, both of which are tested in our paper. And here we see HSR using our method to perform object depth estimation and robot grasping using a single RGB camera. To understand how this works, first consider that work in psychology has established for some time that people perceive depth motion from the optical expansion or contraction of objects. In our previous example, laundry objects exhibit optical expansion as HSR's grasp camera advances. If these objects are segmented, we can track this expansion in the camera's image plane. And if we know the relative camera movement between observations, we can solve for the object's depth. Our optical expansion model consists of an object, a pinhole camera, and a projection of that object onto the camera's image plane, which is represented using a binary segmentation mask. We denote the distance along the optical axis from the camera to the visible perimeter of the segmented object as d, and the size of the segmentation mask or scale as L. If the camera moves closer to the object at position d2, the projection of the object onto the camera's image plane and segmentation scale will also change. If the object's distance or depth decreases, the projected scale increases, causing optical expansion of the segmented object. Also note that the object segmentation scale is inversely proportional to the object's depth, so we can relate all observations along the optical axis to a constant. Although the object's depth is unknown, if we can measure the relative distance between two observations, we can find a solution. Let's look at a concrete example. Here, HSR is approaching the sugar box on the ground and has collected two images 0.38 meters apart. After segmenting the sugar box in both images, we need to determine the segmentation scale in each image to relate the observations together. Rather than using a specific length measurement, in practice, it's more straightforward to track changes in scale using area, which can be measured simply as the sum of segmentation pixels. Using Galileo's square cube law to relate area to length, we then calculate the square root of area to measure the segmentation scale. Finally, using the analytic solution from our paper, we are able to solve for the distance to the sugar box d1 using the relative change in camera distance and the relative change in segmentation scale. Using the actual numbers, the object depth is found to be 0.292 meters. With a ground truth object depth of 0.26 meters, this isn't too bad, but we can do much better. Also note that depth estimation errors are primarily caused by noisy segmentation in the real world, which causes the estimated segmentation scale to deviate from the ground truth. One way to increase the robustness and accuracy of the depth estimation result is to use additional intermediate observations. Let's look at the same example, but with 8 intermediate observations added between the previous two images. To take advantage of all 10 observations, we will use a least squares formulation that relates all relative camera position z and segmentation scales L to the object depth at camera position 1. Using the numbers from all 10 observations, the object depth at d1 is estimated to be 0.272 meters, which is about a 2/3 reduction in error from the previous two observation solution, and is more than accurate enough to use for 3D perception and robot grasping. However, it's important to keep in mind that object depth estimation can be much more challenging than this example. Let's look at an example with fewer observations within a smaller camera movement range, a smaller target object in a cluttered environment, and a noisier segmentation mask resulting in a less reliable measurement for changes in scale. Using the least squares solution in this new setting, we get a depth estimation error of over 0.1 meters, which is no longer accurate enough for robot grasping of an object as small as the marker. This is where one of our primary innovations in this work really distinguishes itself. Imagine if instead of being locked into a single modality for estimating depth, such as a single measure for estimating changes in scale, we're able to incorporate countless features from the raw segmentation masks and relative movement distances, and even ignore incoming data that are erroneous. In this work, we train such a network that learns to perform these considerations automatically, mitigating errors associated with real-world segmentation and providing a reliable estimate for object depth from motion and segmentation. Returning to our previous example, we use the binary segmentation masks M and relative camera movement position Z as a network input. In this way, our network learns to estimate the depth of segmented objects without any reliance on application-specific appearance data, whether from the foreground object or background, which increases generalizability. Our network outputs the estimated depth of the segmented object, which, despite the difficulty of this particular example, is accurate within a half centimeter of the ground truth object depth. Compared to the least squares solution, this is a significant reduction in error and enables our learned object depth model to reliably perform 3D perception and real-world applications. Furthermore, because forward passes of our network are fast compared to the time it takes to collect new images, we can improve overall depth estimation robustness by combining multiple depth estimates over permutations of all collected data. To train our object depth estimation networks, we develop another necessary innovation, the object depth via motion and segmentation dataset. ODMS training data are extensible through the use of continuously generated random synthetic objects, which are also randomly distanced from the camera with their segmentation masks correspondingly resized. Let's look at the process of how we generate random objects for ODMS training. The first thing to note is that ODMS training data is configurable through the use of random parameters. When generating random objects, the object size is selected randomly from a set of possible values, as well as the number of points that we will use to generate the object's contour. From these two random parameters, NP contour points are randomly selected from the bounds determined by the object size SP. Let's look at a concrete example. Here, SP is selected to be 100 and NP is selected as 5. Given a uniform distribution between 0 and SP, the x and y position of each contour point is then randomly selected. Next, we complete the contour using Bezier curves with randomized smoothness, and then select the random camera distances that will determine the object's ground truth depth and segmentation scale. The configurable parameters for randomized distance are the minimum and maximum depth, the minimum camera movement range, and the number of input observations. Using these parameters, the endpoint observation distances Z1 and Zn are randomly selected from a uniform distribution, with the remaining observation distances randomly selected between the endpoints. Once these random distances are determined, we scale a segmentation of the random object according to its depth using our optical expansion model. Here, we show the object being scaled into segmentation masks at the minimum and maximum depths. Using this process, the ODMS dataset continuously generates new label training data. These data are configurable to a specific application, but each training example is randomly generated, making each object unique to avoid overfitting. We also develop and evaluate 3 unique approaches for training object depth estimation networks. Our first approach is direct depth estimation, where the network learns to directly predict the absolute object depth given a series of observations. The main benefits of this approach is that it is relatively straightforward, and it enables the network to learn what range of depths are reasonable for a specific application. Our next approach learns to predict normalized object depth using a normalized relative distance input. Because this network predicts object depth relative to the camera movement range, its dimensionless prediction is more broadly applicable. Our final network learns to predict the relative change in scale between the first and last observations, which we use within our optical expansion derivation to solve for object depth. The benefit of this approach is that the network's prediction task is simplified while remaining dimensionless and broadly applicable. To evaluate each approach and establish a benchmark for the ODMS dataset, we developed 4 validation and test sets that include over 15,000 examples across multiple domains, including robotics and driving. One of the first things that we find from the test set results is that all 3 of our ODMS trained networks outperform the least squares baseline. Although the least squares approach performs well with clean segmentation data, it does not perform well on the test sets with segmentation errors or moving objects during driving. Each network is trained on data with depths and camera movement distances consistent with the robot object, normal, and perturbed test sets. The direct depth estimation network has the best performance on these 3 sets. However, because it doesn't use a dimensionless prediction during training, it has the worst performance on the driving dataset, where the distances for camera movement and object depth are much greater than during training. On the other hand, the generalization of the normalized distance and relative scale prediction networks across all application domains is highly encouraging. It is also worth noting that the relative scale network achieves the best driving and overall result. More results and configurations can be found in our paper. For example, we found that adding noise to segmentation masks during training leads to the best performance on the driving dataset, or including a radial input image for convolution results in a significant improvement for the robot object test set and the best overall performance. Thank you for watching our video. If you're interested in using ODMS in your own work, please visit our GitHub page at the address shown here, and if you want to learn more, be sure to see our paper for more details.